It's a great honor and pleasure to be here today. So I'm going to share with you some of the most exciting discoveries, in my opinion, in cosmology, the study of our cosmos. And I'm going to do it in four parts. First, we're going to talk about what we've learned about space, then about our place in time, then about the origin of it all, the theory of inflation, and finally, the future, both of the cosmos and of the study of the cosmos. Now, to understand our universe, we need to think big. So how big is our cosmos? We humans have again and again underestimated not only the size of our cosmos, realizing that everything that we thought existed was just a small part of a grander structure, a planet, a solar system, a galaxy, a universe, and maybe even a hierarchy of parallel universes. But equally importantly, we've repeatedly underestimated the power of our human minds to understand our cosmos. And that's an inspiring thought that we're going to come back to again and again and again. Let's begin in the Himalayas here, heading off into space. And as we do this, I want to thank the American Museum of Natural History for putting together this beautiful video, which is not just eye candy, but perfectly scientifically accurate with everything to scale. Now, when our ancestors first started exploring the Earth by foot, later with sailboats, they kept discovering that it was much bigger than they thought. Until finally, over 2,000 years ago, Eratosthenes was able to measure exactly how big our beautiful round planet is. How did he do that? Not by flying around the Earth, but just by letting his mind fly and very creatively using angles. He realized that while the sun was straight overhead in one part of our planet on the summer solstice, it was 7.5 degrees away from overhead somewhere else. And he correctly inferred from that that those two parts must be 7.2 degrees away from each other, therefore around the Earth, which was 794 kilometers. So he figured that the way to go, the distance all the way around the Earth then is simply equal to 794 kilometers times all of the 360 degrees divided by those 7.2 degrees, which gives 39,700 kilometers, which is just remarkably close to the modern measurement of 40,075 kilometers. It's better than 1%. He was a bit ahead of his time. Columbus later completely bungled this and underestimated the distance of his travel to India by a factor of 5. So he wouldn't even have gotten funding for that if he had used the correct values. But this is very, very impressive. And since we knew the size of the Earth, it was very natural to ask, well, what's next? When we look farther out into space, when you look at the moon, for example, we must ask ourselves, is the moon something which is relatively small and nearby, or is it something really huge and far away? Either way, it might subtend the half degree in the sky that we observe. Today, of course, we have very high-tech ways of figuring out these things. We can, for instance, using not mental power, but the rocket power that we got from the mental power, put satellites into orbit. We can bounce radar off of the moon and simply measure how long it takes to come back. And by this radar bouncing method, we can measure the distance to the moon now to better than a millimeter and measure the distances to Mars and Venus and other planets. But already way back in ancient Greece, Aristarchus was able to figure out roughly the distance to the moon just with human ingenuity again and the clever use of geometry. He noticed that during a lunar eclipse, when the Earth casts its shadow on the moon, the shadow has a curved edge. And as you can see here, this immediately tells you that Earth is much bigger than the moon. And Aristarchus realized that actually from this, it's 3.7 times bigger than the moon. So then since we know the size of the Earth now from Eratosthenes, now we know the size of the moon. And we know the angle the moon subtends in the sky, so we know the distance to the moon. And indeed, Aristarchus correctly figured out it's 30 Earth diameters away, a huge distance. Now, as we keep flying out into space to even greater distances, what about the other things that we encounter? What about the sun? How far away is the sun? it subtends about the same half-degree angle in the sky as the moon. Is it just a little bit farther away than the moon? Enough to explain why the moon goes in front of the sun during a solar eclipse? Or is it vastly larger and vastly farther away? Well, Aristarchus actually figured this out too, by just considering this triangle here, which has at its corners the sun, the moon, and the earth. He knew that during last quarter moon, when the moon looks half full, this is, of course, the bottom angle is a 90-degree angle. This angle between the moon and the sun, he was able to measure to be a little bit less than 90 degrees. And now, since he knew both the shape of the triangle and also the length of this Earth-Moon leg of the triangle, he could figure out this leg, the distance to the sun. And he figured out that the sun was much, much farther away than the moon, therefore much bigger, and that's why he came to the conclusion that we were probably orbiting around the sun. Unfortunately, although he was a genius, back in those days, they weren't very good at error analysis and estimating the uncertainties in their measurements. And both he and then Copernicus and others, when they, with similar cleverness with angles, figured out the distances to the various planets and built a nice scale model of the solar system, were all off by a factor 20. Only a couple thousand years later did we realize that our whole solar system was actually 20 times bigger than we thought. That's like confusing a doll's house with a real house. Now, as we keep flying out farther and farther away, exploring the full vastness of space, we see our solar system, and then we see these stars in the distance. People always wondered about stars. Great myths were created for what they might be. Maybe they were holes punched in a sphere that light shone through, or maybe they were something else. But I think, as smart as they were, most ancients who thought about this must have felt a little bit melancholy, knowing that they would never really know what the stars were. And in fact, when this famous song was written, "Twinkle, twinkle, little star, how I wonder what you are," they still didn't know what the answer was. Only 30 years after the song was published was this mystery actually convincingly solved through work by the astronomer Bessel and others. And how was he able to do this? How could he figure out how far away these things were? Well, by a method known as parallax. And here's how it works. I'd like you to all hold your thumb up like this, at arm's length, and alternate blinking your left eye and right eye. And then with your other hand, hold it up in the air if you can see your thumb jumping back and forth as you do this. This is parallax. Now move your thumb in so it's much closer and keep blinking. You see how it jumps by a larger angle now? The so-called parallax angle is larger. This is how your brain figures out 3D vision, right? This is how you know how far away things are so effortlessly, because it's all hardwired into your neural circuitry, this parallax method. If you were a giant and you had your eyes much, much farther apart, your 3D vision would be much better. And fortunately, we can act like giants, because if we take pictures from the Earth during the summer and during the winter when it's on opposite sides of the sun, it's like being that big and having your eyes that far apart. We get fantastic 3D vision. And if you take a picture, for example, of the 61 Cygni system, and you look at it, and you flash the July 1st picture versus the January 1st picture, for instance, you notice that almost everything looks the same, except there's something that's moving back and forth, just like your thumb was here, right? That must be closer, that binary star, than the other things. And by measuring the angle with which it jumps, we can measure its distance. And Bessel really impressed his colleagues because this was a vast distance he measured. The distance to the sun is so large that it takes 8 minutes for light to reach us from there. But most of the stars you see in the night sky here in New York are so far it takes hundreds of years for light to reach us from them. Hundreds of years. So someone there looking at us wouldn't see the World Science Festival. They might see, for example, the sale of Manhattan being negotiated with the Native Americans. And moreover, Bessel and the other astronomers knew that how bright something looks depends on how far away it is, with an inverse square law, right? So if you move it 10 times as far away, it looks 100 times dimmer. And he figured out that if you take something as bright as this, as a star, and you were to move it to be as close as the sun, since it looks if it's for argument's sake 10 million times farther than the sun, and it's 10 to the power 14 times fainter, well, when you move it 10 to the 7 times closer, it's going to look 10 to the 14 times brighter, and it will look approximately as bright as the sun. And this gave the first convincing answer to the question of what the stars are. There are these things which are about as bright as the sun. They're distant suns, just like Giordano Bruno had speculated back in the 1600s when he got burnt at the stake for his, as a reward for that. And by looking farther at this, at the data from distant stars, by looking carefully at the spectrum of light that came out in different colors, people were able to not only establish that these are distant suns, but also look at what they were made of and see that they were made of the same kind of gases that the sun is made of, hydrogen and other things, and measure the temperature and so on. And these mysterious white dots, which had really foiled science for so many decades, even when the telescope was invented and people looked at the white dots, they saw white dots again, right? But now there had been this fantastic break, and we knew that these were physical objects. Even though we couldn't go there, by letting our minds fly, we could understand. Let's continue our journey even farther out into space. Raise your hand if you know anybody who was born before 1925. I'm thinking of my grandma right now, and when she went on her first date, this was her universe, the solar system and a bunch of stars. Because it wasn't until 1925 that the mystery of galaxies was actually solved by Edwin Hubble. Until then, these beautiful nebulae that you can see in Van Gogh's Starry Night painting, for instance, it was not known what they were. Some people thought they were just silly little gas clouds out there between the stars. But Edwin Hubble, for the first time, was able to discern that there were actually individual stars in what was known as the Andromeda Nebula. And he had this idea that this was actually an agglomeration of billions and hundreds of billions of stars, which he called an island universe, which we now call a galaxy. And by using the same idea we just talked about, that farther away things look dimmer, and figuring out how many watts of light those stars he saw were actually shining with, and comparing that with how bright they were, he could measure the distance. And again, totally shattered all distance records. We now know that the Andromeda Galaxy is so far away it takes about 3 million years for its light to reach Earth. And that was just the beginning. We can now look at galaxies much farther away. Even if we can't see most garden variety stars in there, sometimes a star explodes in a supernova explosion, which is so violent and powerful that it can outshine the whole galaxy for some days. And we can see it. And we can figure out, by looking in detail at its spectrum and its time dependence, how many watts that was, and then infer how far away this is. And by using methods like supernovae explosions and a lot of other clever techniques, we've been able to actually now figure out how far away vast numbers of galaxies are from us and build up enormous three-dimensional maps of the cosmos. And I had a great fortune and luck in my career to get to work on the Sloan Digital Sky Survey that you see here, which is one of the most ambitious three-dimensional sky mapping projects to date. And again, we've learned that everything we thought existed, now our galaxy, was just a part of an even grander structure. Groups, clusters of galaxies, superclusters, and even enormous filaments like the Sloan Great Wall stretching 1 billion light years. And even this is still not the end of space. Even this is still part of an even grander structure, what we affectionately know as our universe, the spherical region of space from which light has had time to reach us so far during the 13.8 billion years since our Big Bang. So this begs the question, is that it? Or is there still more? Is space still bigger? Does space even go on forever? This is something that I used to wonder a lot about as a kid. And it used to seem to me that just from logic alone, space had to go forever, because how could it not? Now, if it didn't, would there be some sort of a sign you would come to saying like, warning, space ends here, mind the gap? That just sounded way too silly. And moreover, what would be beyond the sign then, right? But then, as I grew older, I learned that Einstein had given us much less silly ways for space to not be infinite. For example, space could be curved, like the surface you see here of the sphere on the left. If you're the ant here, you could just keep walking what seems to you to be a straight line, and eventually you would just come back to where you started. Maybe it's the same with our space, that you just go really far in this direction, and just like in the old Space Invaders computer game, find yourself coming back from the other side of the screen. It's possible, according to Einstein, and it's an experimental question, not a philosophical question. Now, the exciting thing that you see here is that this ant can actually figure out whether it's on a curved surface or not without going all the way around, by just drawing a triangle. If he sees that the angles add up to more than 180 degrees, like he learned in his ant high school, then it's curved. And I've had a lot of fun with my friends and colleagues doing exactly this experiment in our physical space, making the biggest triangle you can imagine, which goes from Earth over to the end of the edge of the universe, off to the side and back. And the most accurate measurements we have show so far no hint of any departure from 180 degrees for the sum of the angles. So we have no evidence there that space is not infinite. There are other clever experiments we can do as well. No evidence that it's not infinite. And moreover, the best theory we have for what created our space, the inflation theory that I'll talk about later, which stretched out and created this awesome cosmos, perhaps, that we're in, it actually predicts that not only that space is big, but it generically predicts that it's even infinite. Now, in summary then, we've repeatedly underestimated both our ability to understand the cosmos and also the sheer size of it. And the edge of what we saw here in our explorations of space is the edge of our observable universe. But what is the deal here? What are all these red, yellow, and blue spots that adorn the edge of what we can see? To understand this, it's not enough to just talk about our place in space. We also have to understand our place in time. And that's what we're going to turn to next.